Okay guys, so here we have a well-insulated compressor accepting nitrogen. It looks like we have the temperature and the pressure given, as well as the volume of flow rate at the inlet. And then we're going to compress that nitrogen, and it's going to exit at a given temperature and pressure. We're told we have no kinetic energy and no potential energy from the inlet to the exit. And then also we're going to be looking for the compressor's power in horsepower, as well as the volumetric flow rate at the exit in cubic feet per minute. So I'm going to drop our schematic here. So we have the compressor, and I'll make it as a trapezoid. And it's well insulated, so I'm going to just add this dotted layer here just to indicate that basically the heat transfer. So we'll have an arrow coming in or coming out. It doesn't really matter. We're just going to say that Q dot equals 0. And we're looking for the input power because compressors do consume power. So we're looking for, we'll call it Wn, the input power, and that's going to be some number in horsepower. Now we have an inlet on the left and an exit on the right. So we'll call this 1 and we'll call this 2, inlet and exit. And so we're working with nitrogen, which is N2. It's a diatomic atom or molecule. And so we have T1 equals 60 degrees Celsius. That's your inlet temperature. Inlet pressure was given as 14.2 psi. We have the volumetric flow rate as well. So V1 equals 1,200 cubic feet per minute. And now at the exit, we have T2. Also nitrogen, of course. T2 equals 500 degrees Fahrenheit. We have P2 equals 120 psi. And then the volumetric flow rate at the exit is what we're actually looking for. So that's some number, and that's going to be in cubic feet per minute. And last but not least, we have that the kinetic energy is equal to the potential energy, which actually equals 0. All right, so to find, the first thing I'm going to do is find the power of the compressor, and in order to find that, I'm actually going to use the energy balance equation over this compressor. So if you recall, that means that we'll have 0 equals the heat transfer minus the power plus the mass flow rate times what comes in minus what comes out. So it's going to be H1 minus H2 for your internal energy or your enthalpy, plus your kinetic energy, which is V1 minus V2, and we're going to square both of those units. I'm also going to add a vector here so we know we're talking about velocity, and divide that by 2. That's just your kinetic energy formula, plus your potential energy, which is going to be gravity times the change in height, so Z1 minus Z2. And this here is your energy balance equation. Now we can further simplify it because we were told that it's a well-insulated compressor, so we have Q equals 0. The heat transfer is negligent. And then also the kinetic and potential energy were also called out to be neglected. And so therefore we have that if we just rearrange this and add power to both sides, we'll have that W dot equals the mass flow rate times H1 minus H2. Now, on a standard property table, we don't have the enthalpy, but we can rearrange this or rewrite this as the power W dot equals mass flow rate times, if you recall, you can break down this unit here into the specific heat of nitrogen times T1 minus T2. And these are actually going to be equivalent expressions. So with this formula here, we do have T1 and we have T2. However, we don't have the mass flow rate, and then the specific heat is just a constant, and I'll pull that up in a second. But to find the mass flow rate, I'm going to use the ideal gas law. So if you recall, you'll have that P1 V1 equals mR T1. And if you rearrange for the mass flow rate, you're going to have m dot being equal to P1 V1 divided by RT1. And so now let's plug in what we have. So we have m dot equals, so the pressure was 14.2, and that was pound force per inches squared, PSI. And we're going to look for, we know that the final unit we're looking for is going to be in feet, cubic feet per minute. So I'm actually going to convert this into feet. So we're going to have 144 inches squared per 1 foot squared. And now we have pressure per square foot rather than pressure per, PSF rather than PSI. And now we have the volumetric flow rate, so we have 1200. Next we need is our gas constant for nitrogen. So to refine to the gas constant, we just have the gas constant R equals the universal gas constant divided by the molecular weight. So the universal gas constant in English units is equal to 1545, and the unit is actually in feet pound force, so foot pound force, which is the unit for work, divided by pound mole degree Rankine. Think of it kind of like your kilojoule per kilogram Kelvin, except this is the English equivalent. And our molar mass is just simply 28.013, and that's pound mass per pound mole. And we can make some cancellations here. Our pound mass and pound mass are going to cancel out, and we'll have that our gas constant R equals 55.15, and it's going to be foot pound force per pound mass degree Rankine. All right, I went ahead and added that into our formula for the mass flow rate. And last we need is T1, which is the temperature. So it looks like I actually wrote Fahrenheit here, so this, or Celsius, this should be 60 degrees Fahrenheit. So to get from 60 degrees Fahrenheit to Rankine, you just add 460 degrees. So we have 520 degrees Rankine. And now we can cancel out some units here. The Rankine and Rankine will cancel out. And then we have square feet here, so we could get rid of the exponent here. And next we can cancel out the feet as a whole from the numerator and denominator, and the pound force and pound force will cancel out. Inches squared will cancel out, and you're left with pound mass and minute. So the minute will drop down to the bottom, and the pound mass will go into the numerator, so we know we did this correctly. And if you calculate this out, you'll actually have that your mass flow rate equals 85.56 pound mass per minute. And so now we can plug that into here. So we'll start this going here. So we'll have the power equals 85.56 pound mass per minute. Now we need our specific heat. So our specific heat for nitrogen is just going to be 0.249, and this is English units, of course, BTU per pound mass degree Rankine. Again, think of that like your kilojoule per kilogram Kelvin. And now we need our temperature difference. So I'm going to multiply that here on the next line times T1, which is again 60 plus 460 would make it 520 degrees Rankine, minus T2, which is 500 Fahrenheit or 960 degrees Rankine. And now, as you can see, these Rankines will cancel out your Rankine right there. And your pound mass is going to cancel out, and you're going to be left with BTU per minute as your unit here. So we'll have that the power equals negative 9374.22 BTU per minute. And it's a good thing that it's negative, because that indicates that this compressor is drawing power rather than generating power. And so we know we did this correctly. And so now we need to convert into horsepower. So we'll use some stoichiometry here. So we have negative 9374.22, and that's BTU per minute. And now we're going to multiply that. I'm going to use the conversion factor of 2545 BTU. We have 2545 BTU per 1 hour, and that equals 1 horsepower. So that's our conversion factor. And so now I need to cancel out our BTUs, but now we have minute and hour. So to get rid of that, we're going to multiply by 60 minutes per 1 hour. And if you do, your hour and hour will cancel out, minute and minute will cancel out. And as I can see, you are left with horsepower. So if you plug this into your calculator, you'll have that your W dot equals negative 221 horsepower. All right, next up is the volumetric flow rate at the exit. So recall that we use the ideal gas formula of P1V1 equals MRT1. Now, if we were to take the mass flow rate, because we know that mass flow rate is conserved from inlet to exit as it's a single inlet, single exit control volume, we'll have that m dot 1 equals m dot 2, and the gas constant R is equal on both sides as well. So if we divide both sides by T1, we'll have that P1V1 over T1 equals MR, and MR is equal on both sides. So therefore, we can have the expression of P1V1 over T1, which again equals MR, must equal P2V2 over T2. It must make sense because the mass flow rate and the gas constant are conserved on both sides. So with that being said, I'm actually going to go ahead and fill in what we have here. So for our pressure, and I'm going to keep this all in feet, by the way. So for our pressure on the left, we had 14.2, and that was pound force per inch squared. Again, converting into feet, we have 144 inches squared per 1 foot squared. Our volumetric flow rate was 1,200 cubic feet per minute. And now we can divide it by our temperature. So our temperature was, again, 520 degrees Rankine. Set this equal to the right side. So on the right side, we had 120 psi, so pound force per inch squared. And that's going to have a conversion factor of 144 inch squared per 1 foot squared. I apologize for doing this, but we're going to multiply this now by V2, your volumetric flow rate 2, which is actually our unknown. And we're going to divide all of that by 960 degrees Rankine. So now if you were to rearrange and solve for your V2, you'll actually have that your Rankine and Rankine is going to cancel out since you're going to multiply both sides by 960 degrees Rankine. And if we divide now, your pound force and pound force cancels out. Of course, your inch squared cancels out as well. And then your feet squared and your feet squared will cancel out. And you're going to be left with this unit here of feet cubed per minute. So we know we did that correctly. Now, if you actually numerically plug this into your calculator, you'll have that V2 equals 262.15, and of course in cubic feet per minute.